Good morning, everybody. Welcome to the session. So, in this session, we are going to continue to learn about the alternating voltage. In the previous session, we learned about how we can generate the alternating voltage and the alternating current. So we took an example where we had a conductor in a magnetic field of flux density B, and we had a conductor of length L, and this conductor was rotated inside a magnetic field with the linear velocity of V, or angular velocity of omega. So when we are rotating, as we saw, at different positions, the amount of flux linked with the conductor was different, and as per the flux linkage, the amount of EMF induced also changed. So whenever it was maximum flux we had near the poles, then EMF induced was maximum, and when it is away from the pole, the flux linked is zero and EMF is induced zero. So one rotation of the conductor will generate a one sinusoidal voltage, and when conductor continues to rotate, that is how we'll get the subsequent sinusoidal cycles. That is how the alternate voltage is generated. Now, how to represent the alternating voltage? One thing was we drew the waveform, and there is a way we can understand the alternating voltage. When we are drawing the waveform, we should know what is the peak value, right, of the alternating voltage or the current Vm or Im. We should know the peak value, and we should know the frequency or the time period. So that is how we can draw. The time taken for one cycle is called as a time period, and that time period has to be the peak value has to be represented on the waveform. That is the one way of representing. Second way of representing alternating quantities is using the mathematical equation. So all the alternating voltages, they take the mathematical form of V is equal to lowercase v is equal to Vm sin omega t, or V is equal to Vm sin theta, or V is equal to Vm sin 2 pi ft. That is the form it will take. And similarly, current will have similarly I is equal to Im sin omega t, where the lowercase I is the instantaneous value and Im is the peak value of the current. Now, those are the two representation. In spite of being easily represented in a mathematical form or in the waveform form, but still it is very difficult to understand. So intuitively, we cannot understand what is the amount of the voltage. So for that, there were alternate representations were proposed. One of the representation is the average value. So average value, you understand what is the meaning of the average? Suppose you have 5 samples, you will add those value and divide it by 5. For example, you have 5 subjects and you have scored certain amount of marks in each subject. If I have to tell, instead of telling all the subject values, you can represent your result as one value, that is an average value. So what you will do, you will add up all the marks for the individual subject, and there are 5 subjects, you will divide by 5, you will get the average value. Similar to that, in case of a waveform, okay, in one particular cycle, I can have many instantaneous values, right? For instant t1, t2, t3 and so on, I can have a instantaneous voltage lowercase v1, v2, v3 and so on. And what would be the average value? V1 plus v2 plus v3 plus so on, divided by how many time slices I have made, t1, t2, t3 so on, tn. So divided by n, that will give me the average value. But the problem with this kind of a calculation is, we know the sinusoidal waveform, the positive half cycle is exactly same as the negative half cycle. So if you try to add all the values at different instance for the positive cycle and negative cycle. If you add them up, what it will become, it will become 0, because positive cycle is exactly same as the negative cycle. We get the average value as a 0. So uh, that is the reason when we are taking, when we are representing the average value of a sinusoidal waveform, we take only the half cycle, that is the positive cycle. In half cycle from 0 to pi, we take all the instantaneous value divided by samples that we have taken, that will give the average value. There is another way to calculate the average value. Average value of a sinusoidal waveform is equal to the whatever the total area under the half curve divided by the time period. Okay, so average value average value is what? Value of the waveform is the average of all values over a period of time. So as I told you, we consider the time period as just the half cycle for the sinusoidal waveform. Why half the cycle? Because sinusoidal waveform is a symmetrical waveform. And what is a symmetrical waveform? Symmetrical waveforms are those waveforms where the positive cycle is exactly same as the negative cycle. So the average of over one cycle, it will become 0. That's why we take only half cycle. And this statement is true for any kind of a symmetrical waveform. Means the positive cycle is same as the negative cycle. If it is a non-symmetrical waveform, then we will take the average of the complete cycle. So therefore average value is equal to total area under the curve for time t. Means whatever the area, I will show you the waveform, what area we are talking about, we will see, and divided by the time period. So in this case, would be the half cycle if it is a sinusoidal waveform. So in case of a symmetrical wave, that is sinusoidal voltage or current, the value over one cycle is 0, because positive cycle is same as cycle. It is because positive is equal to the negative half cycle, so that net area is 0. In case of unsymmetrical, non-symmetrical waves, for example, half wave rectifier. So in case of a half wave rectifier, we have only the positive cycle, and during the next half cycle, the voltage or the current is 0. So again, positive cycle I will have, next half cycle will be 0. So that is a one example of symmetrical waveform. If it is a symmetrical waveform, as I told, the average value is equal to area under the curve for one complete cycle divided by the time for one complete cycle. So that is how we will calculate. And okay, average value of a sinusoidal current or a voltage, the average value of a alternating current or voltage over one cycle is 0, because positive cycle is equal to negative cycle. So both cancel each other. So that already we have seen. Therefore, for the alternating symmetrical cycle, we take the half cycle average. So how to calculate the half cycle average? The half cycle average value of an alternating current is value of the direct current which would send the same amount of charge through a circuit for a half the time as sent by the alternating current through the same circuit in the same time. We'll try to understand what that means. Okay, so we already, from mathematical perspective, we already understood what is a half cycle average. What is the half cycle average? It is one definition is all the instantaneous values summed together divided by number of instances. That's one. Or I will take the area of the half cycle, area under the curve for the half cycle, and divided by the time period. So I will get the average value. But actually, the actual meaning in terms of electrical engineering, the meaning of the average value is this value is equivalent to a direct current, okay, which will send the exact same amount of charge. Suppose you have a direct current. Let us say we have a alternating current applied to one circuit. and in half cycle it will move around x amount of charges through the circuit. So it will make x amount of charges to flow in the circuit. Suppose I have another DC circuit, okay, DC value, and that DC value also makes the same amount of x amount of charges to move in the circuit for the same half cycle time. Then that DC representative, DC current means DC value, that is a representative of the average value of the alternating current. Means what? The average value of a alternating current is equivalent to DC current, which will make same amount of current to flow in the circuit. So that is how we define. So once again, you can will read this. Half cycle average value of a alternating current is value of the direct current. So this is the value of the direct current, which would send the same amount of charge through the circuit for the half the time as sent by the alternating current through the same circuit. So in the same time, that is how we interpret in terms of electrical engineering. That is the meaning of the average value. And how average value are represented? We represent the average value with the capital I and suffix AV. So IAV represents the average value of the current. Capital V suffix AV represents the average value of the voltage. Now we'll try to find the average value of the sinusoidal waveform. This is the sinusoidal waveform we have. This is a representative of the current. This is the I. Y-axis is I, the current, and x-axis is represented in the angle, that is theta. And this is the waveform, and this is the peak value. Peak value, that is Im. And mathematically, this is the waveform representation, and this waveform or this current is represented as I, lowercase I is equal to Im sin theta. Now we have to find the average value of this particular alternating quantity. What we will do is, so the first is this is symmetrical waveform. The formula we are going to use for calculating the average is average value is equal to area under the curve. So you can see this is the curve, okay, and this is the area under the curve. So we will find the area, total area under the curve for half cycle divided by the time period for the half cycle, that is pi. So how to find the area of this particular half cycle? We will take a very small strip, d theta, very small strip. Then the width of that strip is d theta. The height of that would be instantaneous value, that is I. And we are taking this strip very small. This length and this length are almost equal. So what would be the area? You can consider it as a rectangle. The area would be, area of this strip would be I into d theta. So once I have this strip, what is the area? I into d theta. If I integrate I into d theta over this period, that is from 0 to pi, then I will get the complete area. Okay, so that is how the derivation is done, and this derivation is very important from the exam perspective. So you can see here area of the small strip, the small strip that we have taken here. This is the small strip. Area of that strip is given by I into d theta, because we are considering it as a rectangle. That's why area of the rectangle is like L length into width. So that's why I into d theta. And if I want to calculate the area of the half cycle, then I will integrate this from 0 to pi. That you can see. So area of one half cycle, 0 to pi, I d theta. And what is I? We know I is Im sin theta. And in this, Im is constant, right? So I will take out the Im outside. And integration of sin theta is what? Minus cos theta. minus cos theta and 0 to pi. This will get me a value of cos of pi minus cos of 0. Minus 1, that is minus 2 into minus is 2. The area of the half cycle, I get it as 2im. Now, what is the average value formula? Area of the curve under half cycle divided by the base length of the half cycle. This area is, we calculated im, and what is the base? That is pi, right? Up to this is pi. This width of this time frame is the pi. So what we get, I average is equal to 2im divided by pi, that is represented as I average is equal to 0.637. 1 second, please. All right. So that is how 2 divided by, we get it as 0.637. So this is how we calculate the average value. If I know the peak value of the alternating current or the voltage, then average value of that particular alternating current is 0.637 times the peak value IM. Hence, half cycle average value of AC is 0.637 times the peak value of an alternating current. So for positive half cycle, I average is plus 0.637 IM, and for negative half cycle, we get it as minus 0.637 IM. Now we will take some problems and try to solve to find the average. So in the exam, they may not just give the for derivation as a theory question, they will ask this, derive the average value of an alternating quantity. So this is the derivation you have to do, and repeatedly they either ask average value or the RMS value. Two derivations are there. One of that will be asked, most frequently it is asked. Now this is the given waveform. Any they might give any waveform, and they might ask you to find the what is the average value. So you can use the same principle. Average value is what? For symmetrical waveform, waveform means what? Positive half cycle is same as negative half cycle. Then average value is equal to area under the curve for half cycle divided by the half cycle time period. If they have given the instantaneous values, then you can use the instantaneous values divided by number of instants. And if it is a unsymmetrical waveform, then you have to consider it for the complete cycle. For example, you can see here, this is the waveform. If you see this waveform, on the positive side, it is plus 15 volts. So this is plus 15 volts, and this is the time in seconds. From 0 to 0.2 second, it is plus 15 volts. At point 2, the voltage will reverse its direction, and it will be minus 3 volt for next 0.4 second, that is 0.2 to 0.6 second. Now if you see here, this is the complete one cycle, right? The same thing will repeat here, that is 0.2 is the positive cycle and volt is the voltage. Again, so you will see the cycles. Now this is a symmetrical waveform or unsymmetrical. What type of waveform it is? It symmetrical waveform or unsymmetrical form? Anybody?
Symmetrical waveform.
Is it symmetrical? Symmetrical means what? positive half cycle is same as the negative half cycle. So here, do you see the positive half cycle is same as negative half cycle? No, right? The positive half cycle is not same as the negative half cycle. So this is a unsymmetrical waveform. In case of an unsymmetrical waveform, for calculating the average, we will take the complete one cycle, that is from 0 to 0.6. So we'll see how it is solved. One cycle waveform is 0 to 0.6 second. So the one cycle is from 0 to 0.6 second. V average is equal to area under one cycle, because we are considering it as because it is an unsymmetrical waveform, we have to consider one cycle. So area under the curve, so this area and this area for one cycle, area under one cycle divided by time period for the one cycle. This is the time period, that is 0.6 seconds is the time period. So either you can do this integration. Okay, you can take a small strip, that is 15 into a dt. You can take a small strip as a dt, and you can integrate from 15 dt, integrate from 0 to 0.2, and here another small strip dt, minus 3 into dt, integration from 0.2, 0.2 to 0.6. Or you already know that this is a rectangle, this is one rectangle and this is another rectangle. We can easily calculate the area of a rectangle. Area of the rectangle is this side multiplied by this side, that is 15 into 0.2. This is the area, and area of this rectangle is what? Minus 3 into 0.4. So that is how we will get the total area. So 15, so which will result in the same thing, whatever I explained, because both are rectangles, you can calculate. So what is the value you get is, you will get it as a 1.8 volts. So sum, the total area, what you get is 1.8. So then average value is the area under one cycle divided by the time period. And what is the time period? 0.6. So 1.8 divided by 0.6, it will get it we will get it as a 3 volt. So this particular waveform is equivalent of a DC of 3 volt. Okay, so let us say instead of having this waveform, if I had a direct current, so that would be the represented as a 3 volt. Means whatever the amount of charge, if I apply it to the certain circuit, this waveform, let us say it moves x amount of charges, then if I apply this voltage for 0.6 seconds to a circuit, x amount of charges will move. If I apply the direct current with 3 volts, okay, that is the average value, 3 volts, and for 0.6 seconds, it will result in the same x amount of charges to be moved in the circuit. That is the meaning of the average value. Next waveform, can you try to find the average value for this? First of all, let us consider how the waveform, what is the one cycle, excuse me, the one cycle, this is current, representative of the current. At 0th second, it is 100 milliamperes, and for next 5 seconds, it is 100 milliampere. Then next 2 seconds, it will gradually decline and it will become 0, and this is 7, 8, 9. In next 1 second, that is at second 8, it will go to the maximum value in the opposite direction, that is minus 50 amperes, and next 1 second it will reduce. So it forms a triangular negative cycle. Then it will keep on increasing up to this is 9 and this is 12. Okay, so up to that time, next 3 seconds, it will increase and it will reach 100 milliamperes. Then for next 5 seconds, so this is 11, I think. Okay. For next 5 seconds, it will be 100 milliamperes. Then it will become 0, and for next 4 seconds it is 0. And if you see here, the this cycle will repeat. Now it is 100 for 5 seconds, it is 100 milliamperes. Then so you can see this is the end. What is the time period? Time period of this particular waveform is 20 seconds. So this is from here to here, this is one cycle. So first question is it symmetrical waveform or the unsymmetrical waveform? What kind of a waveform it is?
Unsymmetrical.
Very good. So negative cycle is not same as the positive cycle. So for calculating the average, we will consider the whole time period. So average of this waveform is total area under the curve for one cycle divided by the time period for the one cycle, that is 20. What is the area that we have here? Area under the curve. For here, you can just you can divide the complete area under the curve as A1, A2, A3, A4, A5, and A6. A1 is a we have a this is a rectangle. Then A2 is a triangle. Okay, rectangle triangle. Then this is another triangle A3, A4 another rectangle triangle, and then we have another rectangle. Okay, then we have this rectangle is 0, area is 0. So we have area A1, A2, A3, A4, A5, and A6. A6 area is 0. Can you try to find the average value? I will give 5 minutes. You can try to find the average value. So what is the average value of this? The average current IAV is equal to area under the curve for one cycle divided by time period for the one cycle. And area under the curve for one cycle is A1 plus A2 plus A3 plus A4 plus A5. So wherever there is a negative sign, you have to use that negative sign. Okay, and divided by total time period for one cycle is 20 seconds. Please calculate the average value. So you are being asked to find the average value. First thing you have to understand is, first identify what is one cycle, where the one cycle ends. How to identify that? The same pattern will repeat next, that is the next cycle. So you have to find the where is the beginning of the cycle, where is the ending of the cycle. And once you identify the one complete cycle, then second thing is you have to identify whether it is a symmetrical waveform or unsymmetrical waveform. If it is a symmetrical waveform, you have to take the average for the half cycle. Okay, that is area under the curve for half cycle divided by time period for the half cycle. If it is an unsymmetrical waveform, you have to take area under the one complete cycle divided by the time period for the one complete cycle. Try to solve. See, when you are finding that area, there is no unit for that area. Okay. The unit will come when you do the average value is equal to area divided by the time period. Anybody got the average value? You can just say it or put it in the message section. 57.5, I think that is correct answer. Anybody else got 57.5 milliamperes? So you have to take the unit from here. Okay. This is the alternating quantity. In this case, it is a current. Anybody else got the answer? Shifa? Okay. You can take one more minute. Okay, we'll scroll through the answer. Now we have identified the area here, A1. So we'll calculate the area. So area first is the beginning of the cycle is 0, end of the cycle is 20 seconds. And this first area we have taken a perpendicular line here. So we get a one triangle and one perpendicular triangle and one rectangle. So area of the A1 is this side, that is 100 milliamperes, 100 into this is 5. So 500. And we know that what is the area of the triangle? Half will be, right? So A2 is equal to half, then 2, that is 7 minus 5, 2, and this height is 100. That is 100. So you will get it as 2 will get cancelled, 100 will remain. And when you are calculating the A3, okay, A3 is on the negative side, the height is minus 50. So half 9 minus 7 is a 2. So this width is 2. Half into minus 50 into 2. That is minus half into 2 into 50. We get it as minus 50. Then this area A4, that is this is 11. 11 minus 9. This is base is 2. 2 seconds, and height is 100 milliamperes, and it's a positive value. A4 is what? Half into 2 into 100. 2 will get cancelled, 100 will remain. Then A5, again A5 is what? A rectangle, 100, and this width is 16 minus 11, that is 5. 100 into 5, 100 into 5, 500, and this area is 0 because the height is 0. 0 into 4, that is 0. Therefore total area is how much? Total area is A1 plus A3 plus A4 plus A5. So if I add all those things, we get it as 1150, and average value is equal to total area, that is 1150 divided by 20 seconds, because time period for the one complete cycle is 20. That you get it as 0.0575, that is 57.5 milliamperes. That's how we calculate. Okay. Next representation. Okay, 57 point. Good. Okay, at least. So please, those who didn't get, try to calculate. So they can give it for any kind of a waveform. So whenever they ask you to find the average value, first thing is find out where is the beginning of the cycle and where is the end of the cycle. That is the first thing. Once you know the cycle, complete cycle, check whether the positive cycle is exactly same as the negative cycle. If answer is yes, then it's a symmetrical waveform. Then you have to apply the formula. Average value is equal to area under the curve for a half cycle divided by the time period for the half cycle. If the cycle, if the waveform is unsymmetrical, that is positive cycle doesn't match the negative cycle, then it's unsymmetrical. That time average value is equal to area under the curve for one complete cycle divided by the time period for the one cycle. So that is the how we represent the average value. But the most of the time, like whatever the representation you see for the alternating voltage, this is root mean square RMS value. So there are inherent disadvantage with the average value. It is not a true representation. So true representation of the amount of electricity. That's why there is another representation that is called as a RMS value or the root mean square value. The RMS value of an alternating current or voltage is the value of the DC current when flowing through a given resistance for a given time period. Same amount of heat is produced by the alternating current when flowing through the same resistance for the same time. So here you can see what is a RMS value. RMS value is equivalent of a DC current. Okay, equivalent of a DC. If we connect to a particular circuit, it will generate a X amount of heat. If we connect it to a resistor, it will generate the X amount of heat. The same amount of heat would be produced by the alternating quantity for the same time period. That equivalent DC current is called as the RMS value of a alternating current. Okay, let me repeat again. You have one circuit, you have a resistance, and you are connecting a alternating voltage, and you are checking for some time period t. When you connect the circuit for the time period t, the amount of heat generated by the resistance, amount of heat generated in the resistance is X. And if you take another circuit, similar circuit, same resistance, everything, you put the DC current, and for the same time period t, you keep it connected, and current will flow and it will produce the same amount of heat, that is X amount of heat. Then that DC voltage is called as the RMS value of the alternating current. Okay, that is how it is that is the meaning of the RMS value. Now again, derivation of this is very important from the exam perspective. They will ask derive the RMS value of an alternating quantity. So when we are doing the derivation, it goes in a very similar manner with what we did for the average value. Only difference is here is we have a squared wave. You can see here root, mean, and square. So we take the square of the waveform. So here what we do is this is my waveform. This waveform is I is equal to Im sin omega t, or I is equal to Im sin theta. Excuse me. And whatever the values are here, instantaneous values, let us say t1, t2, t3, t4, so on, this has broken, then I will take the square of that. So here 0 square is 0. Let us say this is 1 ampere. Square of 1 is 1. Then here it is 2 ampere. Square of 2 is 4. Similarly, I have 3 ampere. Square of 3 is 9, and so on. And what is the value of the current here? Instantaneous value of current, that is Im, that is the peak value. The and I have to take the square of that, that is Im square. So what I have, this wave is I is equal to Im sin omega t, and this is I square waveform. What you see on the top, this is I square waveform. And if you see the negative cycle, now I'm going to take the square of all these negative values. The second half cycle is also exactly same as the first cycle. So it will have the same values. This is Im square, and it will become 0. So I will have the squared waveform like that. Now I have to find the I have to find the RMS value. Okay, I have taken the squared value, and I will take the I will find the area. Okay, area. In this case we can take the area for the half cycle, because both are the positive cycle. What is the first equation of the RMS value? RMS value is, if I take the instantaneous value, here I1 square, I2 square, so on, the RMS value is equal to square root of I1 square, I2 square plus so on, In square divided by n. N is what? Number of the instance. So if I have n instance here, that is the n value here. How to find the RMS value? Square root of sum of all the squares of all the samples divided by the number of samples. So in terms of the area, how do we calculate? Area of the half wave, area under the squared waveform for the half cycle divided by the half cycle time period. Because why we are taking half cycle? Because both are positive. So even if I take it full cycle, it doesn't matter. Only thing is I get it as two times. Okay, in the denominator and in the numerator also I get two times, which will get cancelled. So RMS value is the area under the squared waveform. So this is the area under the square waveform divided by the time period and square of the whole thing. So what is the area? What is the RMS value? RMS value is square root of area of the squared waveform for the half cycle divided by the half cycle time period. Now, same way, I is represented as I is equal to Im sin theta, and we are going to take a small strip. Okay, you can see here a small strip d theta on the squared wave. So we are taking it on the a squared wave. What is the, and this strip is very thin, so that this and this are exactly the same. We can say both the heights are same. And what would be the area of this particular small strip? The height is I square and width is d theta. So area of this small strip is I square into d theta. Then how to find the complete area of this half cycle? I'm going to integrate this strip from 0 to pi. Then I will get the area of the squared waveform. So area of the strip I square d theta, and area of half cycle of the squared wave. So if I want to calculate the area of the half cycle, then I have to integrate I square d theta from 0 to pi. So similarly, if we simplify this, I is nothing but Im sin theta. Therefore, Im square sin square theta into d theta. Im square is constant, so it will come out. I have 0 to pi sin square theta into d theta, and we know that sin square theta can be represented as 1 minus cos 2 theta divided by 2. So you can see here cos 2 theta is equal to cos square theta minus sin square theta, and we know that sin square theta plus cos square theta is equal to 1. Therefore cos square theta is equal to 1 minus sin 2 theta, and uh, that is how we get here 1 minus cos theta. Sin theta is equal to 1 minus cos 2 theta divided by 2. Now integrating this, now we have one half you can take out. This is a constant. What we left is 1 minus cos 2 theta. Integration of 1 is theta, and integration of cos 2 theta is sin 2 theta divided by 2, and 0 to pi. If I put the pi value here, pi minus 0, and sine of 2 pi is 0, minus sine of 0 is 0. So on this side it is 0. What we left is with the pi. So what is the area I get? The area of the squared waveform is Im square pi divided by 2. Now we have the formula. What is the formula for RMS value? IRMS is equal to square root of area of half cycle squared wave divided by half cycle base. And what is the area? Area is Im square pi divided by 2. Pi into Im square divided by 2, and half circle base is pi. This pi will get cancelled. Square root of Im square divided by 2, that is Irms is equal to Im divided by root 2, or 1 by root 2 is 0.707. So therefore the RMS value of an alternating current is represented as 0.707 times the peak value. So what is the average value? I average value is equal to 0.637 times the peak value. If it is current, IRMS is equal to 0.707 IM. If it is a voltage, VRMS is equal to 0.707 VM, peak value of the voltage. So this is how we represent the RMS value and the for the current and the voltage, and the representation is capital I suffix is RMS, capital V suffix is RMS. Either RMS value is represented like this, or it will be represented as just capital I and capital V. That is the representation of the RMS value. Now, as I told you, mostly all the electrical representations are in the RMS form. Whatever the equipment you see inside your house, what is the voltage that has been written on that is the RMS value. Okay. Uh, now, we know that your household connection is, let us say, 230 volts. So that 230 volt is nothing but a RMS value. Okay. Now the task is, can you find the mathematical equation of your household connection? Okay. Try to find out the mathematical equation for your household connection. Whatever the voltage that your household has, 230 volts, it is a RMS value.